thank the organization for inviting us, and especially a special thank to Marta that gave us the opportunity to be in touch with this very nice community inside the framework of the Smart Cut Cost Action that I spent a few words later on that. And oh, this is just a few words on my institute. We are here in Naples, the south part of Italy, and my institute work on almost whole topic related to combustion, from standard fuel to renewable fuel to waste and solids, and on the diagnostics and characterization of pollutant and system for pollutant abatement. We have 56 permanent staff, but in the next year you will not be able to hear anymore by Istituto di Ricerche sulla Combustione, because we CNR, that is National Research Council, to which we belong, is merging our institute with other three institutes: Istituto Motori, Istituto Macchine, okay, for Earth Motion. In a new institute will be related to science and technology of sustainable energy and mobility, and we will have about 150 permanent staff. So the through line, I come back to the title of my presentation. The through line of my presentation will be why, when we have all the scenario that push on the deployment and the use of renewable energy, we have to still talk about combustion, and which are the requirements that combustion technology has to face with to deal with the requirement of all the scenario we have on climate change, and a way to approach this point, and a particular unit we are developing on that. What is why we talk about combustion? And we know that in the future energy scenario, the variable renewable energy have to play the main role. But we know that they are not for free, because and there are several drawbacks. The one that everyone knows is the intermittency of renewable energy, but one that is rising lately in last period is the problem related to the metals that are technology enabling substances, because we need plenty of metal, for example, permanent magnet in a nacelle of windmill, and rare earth in photovoltaic and solar cell, of course, lithium in battery. And we have, for sure, the global reserve does not cover the needs, but also the mining technology are not able to mine what we need, and the recycle of critical metals are very is still very low. For most of them, it's not higher than 1%. So it is clear that, of course, we have to face with the environmental preservation, but we have secure the energy supply, because we have to guarantee the ancillary service to across the population, to whatever in everywhere and every time. So of course we have to maximize the energy mix, but the combustion process will not play a secondary role. But we have to think a combustion process as supporting the deployment of renewable energy, because of course they have to face with we have to gain face with different characteristics. Of course, they have to be flexible. The flexibility of combustion process is the main keywords that push on development on advanced combustion technologies. Flexibility in terms of operational parameter, because combustion has to support the variable renewable energy source in their intermittency, and is the only technologies that has the proper characteristics that can assure the effective load following and backup system. And also in terms of flexibility, we have to talk about fuel flexibility. Because you know that because of an environmental concern, the palette of fuel is extending towards biofuels and so on, but also because in this framework, combustion again supports makes stronger the support to renewable energy, because it is very important to store, to increase the sharing of energy, renewable energy, to store the energy during their surplus. And the best way to do this is to store, as told George before, in the energy carrying, chemical energy carriers that has to be used in the combustion system. And this is the framework in which we developed our the cost action on science and technology of smart energy carriers. That is a network that involved 30 countries, and from Serbia we have two university representatives from Serbia, University of Novi Sad with Branislava and Biljana, and of course University of Belgrade, and Marta made a very great job to put in touch and spend a great effort to build our the network. And so, based on that, I will talk on on a specific topic that is one of the advanced combustion technologies that could face with flexibility, both in terms of operational flexibility and fuel flexibility. That is mild combustion. There is a classical definition of mild combustion. The process is mild when the inlet temperature of a reactant mixture is higher than the mixture of the ignition temperature. And so we have to start to reactant that have temperature higher than ignition, and the maximum lower temperature increase during combustion is lower than mixture of the ignition temperature. Well, this is a rigorous definition, but what does it mean in terms of practical point of view? That it evolved from hyperheated, very diluted reactant that are very diluted outside the flammability limits, and that these conditions are reached, locally reached, by means of external or internal recirculation. What are the characteristics of this process? Of course, we need for dilution, especially with internal facility, high turbulence density, and higher, we will have high kinetic times with respect to standard combustion process because we work in diluted condition. And but we reach, due to very low temperature increase during combustion, no very low pollutants level. For sure, we have no soot, but very low, generally in one digit range of nitrogen oxide. It is noiseless because it's very stable, working at temperature higher than ignition one. The most representative characteristic is that is flameless. There is no flame inside the combustion chamber. This is a standard process. Flame processes is a flameless process, mild combustion process. And for these characteristics, the process evolved all over the combustion chamber, where we have almost uniform temperature and species distribution. Okay. So, in general, the facilities that are used for mild combustion are very few, but are based on the internal recirculation, and they make this is some examples that are present in literature. They use a reverse flow for creating the internal recirculation. So generally we have the inlet section and the outlet section of the gases, of the exhaust, on the same side of facility. And in this way, the recirculation, is created in along the main axis of the combustion chamber. But we developed a different one facility that is based on a cyclonic field that is created in a prismatic vessel by means of the injection of fuel and diluent by means of a peer injector and opposite side of the combustion chamber, and we have the output on that side. In this way we create a cyclonic flow, and with this is the burner in operating condition, and we have a quite uniform. This is the temperature profile inside the combustion chamber during working condition. It's very very homogeneous. In respect to the standard combustion process, no flame, and this time these are the range where we are able to operate the combustion chamber. So in terms of flexibility and energy carrier, we explored the use of several fuel, both carbon fuel, the standard one, biogas, and also alcohol, and no carbon fuel too. Let me show shortly some results that highlight the characteristics of this process and this facility mainly. If we look at the results we obtained in propane, I will show you the temperature that we measure inside the combustion chamber. So this is the operative temperature, and as a function of inlet temperature, we can see that we have no combustion below this temperature range. Okay. But if you look at results we obtained starting from an inlet condition diluted for propane for different stoichiometric equivalence ratio, we see that up to for temperature higher than this value, we have stable mild combustion. But when I say stable, I say that each of these points are different working temperature. So in this way, it is not as a standard flame when you are fixed to the adiabatic flame temperature given the inlet condition. You can choose the temperature at which you can work. And this is the characteristics that it also seen with in different conditions, so a lower dilution, also with air. When we arrive, also with methane, when we arrive at this temperature, that if you look at the chemical kinetics of hydrocarbons, it can be identified with the crossover temperature in the kinetic mechanism we are able to use. And so you can able to tailor the temperature in the reactor, and you can choose the temperature to which you want to work. What happened if of course this happened also with very low pollutant level, both for CO2 in green and NOx in blue, for biogas, methane and propane. And we tried to also with alcohol, and we found same situation. We tested ethanol, butanol and methanol in this way, and we have the same behavior. And the last I want to show you is ammonia. Yesterday we talked about that. Ammonia is a very trendy fuel, actually, because several researchers in the field of combustion are focused on this topic, and we had in Lisbon last month the last workshop of our construction focused on ammonia from production to use in combustion device. And why it is important? Why is interesting ammonia? Because it is a CO2 carbon-free fuel, and it is a suitable fuel for storage and transport to storage energy of renewable, and also for transport, because what we learned during the workshop is that there is a very developed infrastructure for distribution of ammonia, also for ship. So it's a very interesting fuel, and but there are several combustion issues, because of course it is potentially a very high NOx emission. It's a very low combustion intensity, because a very low very low heating value. If you see here, so it's very difficult to stabilize the combustion process. Sorry. And so internal combustion process is very difficult to stabilize the flame. What we have is this. We can have stable mild combustion in a wide range of operative conditions. This is the first one, big point. Sorry. But the second one is that in stoichiometric condition, where generally in standard combustion process there is with ammonia a very huge amount of nitrogen oxide formation, we have 100 ppm of NOx. Okay? So, how we can conclude? How I can conclude this presentation? That, of course, energy carrier are very important. Will play a key role in the future energy scenario. That mild combustion is one of the advanced combustion technologies that can support the deployment of a renewable energy source, because it is a very high operational fuel flexibility, and we proved for the first time the flexibility in a wide, with a very wide palette of energy carrier. And it is really operational flexible, because you can have you can tailor the temperature that you want inside the reactor. And mild combustion, same time, always in the framework of SmartCat construction, and we had a joint meeting with an EFC grantee focused on mild combustion. And we will have, we had this workshop in Naples in January after our international conference on smart energy carrier. Very soon we will have a reference website on that. This was a joint decision we had during the workshop. And no picture. Okay, there was this was a picture of we had a new release of the burner that we set on in Cesta Lab. That is one of the largest test rig laboratories for gas turbine in Europe. And we, in collaboration with Baker Hughes, that is a General Electric company. And we had the first OH fluorescence, runner gas-induced fluorescence inside the chamber. Okay. Thank you very much. Sorry for my... Thank you so much.
Grazie tante. We are sorry that we are in the time pressure, so maybe there will not be too much time for questions, maybe one short one from the audience. If not, thank you so much for coming.